Last time we formulated the smoothing spline and solved the smoothing spline by assuming the function f to be piecewise cubic function. So this time we are going to use variational calculus to see why piecewise cubic function is a correct solution for this problem. So first, let's do a quick recap of the smoothing spline. So we are starting with paired data xi and yi. Note that this is a one-dimensional problem, which means that xi and yi are both scalars. So here is the objective function we want to minimize. It has two terms that we want to balance. The first term is the sum of residual square that we use in many regression problems. It tells us how much deviation are there from each point to the curve. The second term is what makes smoothing spline special. It's a penalty term on the curvature. So we're basically balancing the two using the hyperparameter lambda here that controls for the smoothness of the curve. So when lambda equals to 0, that's when we don't have any curvature penalty, and our smoothing spline reduces to a cubic spline that the curve needs to pass through each point. On the other hand, when lambda goes to infinity, that's the time we achieve the solution by pushing the curvature into 0. So the second derivative of f goes to 0. That means the curve we get in the end is a straight line. In practice, we want lambda to be somewhere in between 0 and infinity. So that will depend on the specific problem. It is a hyperparameter we need to tune so that we can balance out the goodness of fit with the smoothness of the curve. Okay, so the main goal of today is to solve this optimization problem directly, where I just rewrite this in a slightly different form, where I defined j of f, where j is something called a functional. J is a functional. So the definition of functional is straightforward. It's just something that takes input of a function and output a scalar. Then we really want to do is to find the best function to minimize this functional j. So how do we do that? So here I'm just going to draw some intuitions and draw some parallels with multivariable calculus, so you can see so you can see how we can solve this problem. So So in multivariable calculus, what we like to consider are functions. So if, for example, g of x, that maps from Rd to R. So these are the elements we would like to consider. This means that x is a d-dimensional vector. Where in functional calculus, what we like to consider are the functionals j of f, where j maps from a functional space to scalar. And then the input of the functional f is a function that lives in this space. So that is the objective we are dealing with, right? So in multivariable calculus, when we want to find the local minimum or local maximum of the function, something we can consider is a directional derivative. So let me just first draw a picture here. So let's say this is our multivariable function g of x. This is the contour of g of x. Then we see that the minimum point is this dot here, right? And So what's special about this dot is that the directional derivative equals to 0. So to translate this into algebra, we can write it in this way. That means the limit of gx plus epsilon v minus g of x divided by epsilon equals to 0. So this is as epsilon goes to 0. So what does this mean is that, for example, imagine that we are at this exact position of this little green dot here, then then no matter which direction we go, we can go to any direction. The function value g does not change. So this must hold true for all vector v. This is true for all v. So that's how we define the directional derivative, and then we can also write it in a slightly different notation with differentials in this way. So we can write it as d over d epsilon of g x plus epsilon v evaluated as epsilon equals to 0. So that's just another way to write directional derivative. And so in functional calculus, we want to draw direct parallel to this, but I'm not able to draw any geometrical picture here. But what we want is that the functional derivative equals to 0. So functional derivative can be written in this way, that except here we are perturbing the input with a function rather than a vector, but it's going to be extremely similar. So we still have limit as epsilon goes to 0, j of f plus epsilon times h. So h is the perturbation function minus j of f divided by epsilon. So that's how we define the functional derivative, except we are perturbing it with a function h. H can be just any random function. So this must hold true for OH. Or we can write it in another notation as d epsilon j of f plus epsilon h evaluated as epsilon equals to 0. So this is the equation we want to solve. And so in multivariable calculus, you probably remember that the directional derivative also equals to the gradient of g dot with vector v. So that must equals to 0 for all v, for all vector v. And the only condition, the only situation this is true means that the gradient vector must equals to 0. So that's the only condition where the directional derivative equals to 0 for any directions we are taking. So for functional calculus, we want something just like this, right? So it turns out we can totally do it, and so in the end we can reduce this equation into this form as something times h equals to 0 for all h. So it turns out we can reduce this equation in this form, and that gives us an equation saying that this something must equal to 0. And this is called Euler-Lagrange equation. I'm not going to write the full form in here, but this is called Euler-Lagrange equation. For this particular video, let's just do things the hard way by starting from this equation right here. Although we can definitely just directly apply the results of Euler Lagrange equation to solve for our functional J of f for the cubic spline, sorry, for the smoothing spline. But for this video, it's totally gonna worth it to do it the hard way. That's where we can see exactly where the kernel functions start to emerge from this problem, from this optimization problem. So let's do that. Okay, now let's write down the limit form for this functional. So we want limit epsilon goes to 0 of j f plus epsilon h minus j of f divided by epsilon equals to 0 for all function h. Write it here for all function h. Okay, so what we can do is we just directly plug in the functional for j of f to see what happens. So we have limit epsilon goes to 0, and I'm just going to write the two terms separately for this. So we'll have summation equals to 1 to n, and then we have yi minus epsilon h of fi square minus. So I'm just going to do this as call this the first term, this is the second term, and then write it out separately. And summation 1 to n yi minus I. So this is epsilon. Okay, I'm just let's go and do this. Okay, so these are the term I just plug in the form of the functional j of f, and then let's just do some canceling here, right? There are a lot of terms can be canceled, so we can see that the first term here let's just call this guy a here. Then we have a minus epsilon h of xi square. And we can actually merge this summation together, and then this becomes a square, right? So when we just expand this square term here, you can see the a square term got cancelled. So that means what we left for the first term is just summation I equals to 1 to n. So the a square term cancelled. So what we got left is 2 times y minus f xi times, let me write epsilon in the front. So 2 epsilon and times h of xi plus, there should be a minus sign in here, plus epsilon square h of xi square. So that's going to be the first term. And for the second term here, let's see, we also can do some canceling because we can first merge these two integrals together. This is actually, second term is actually easier. So we're just going to cancel the f prime prime of x square, and then when we expand it, So this is going to be, we can cancel it this way, right? So it's f prime prime square plus 2 f prime prime h prime prime plus h prime prime square minus f prime prime square, right? So these two will cancel. And what we got is integral a to b 2, I think I'm missing an epsilon here. Okay. And this is epsilon. And then this is epsilon square. Okay, so what we got is 2 epsilon f second derivative of f times second derivative of h plus epsilon square second derivative of h square. Okay, so now let's see that let's see what happens here. So so see here that we have a 1 over epsilon in the front, right? So that's gonna do some canceling as well. And so this epsilon cancels with here, and then we cancel the square, cancel one of the epsilon in the square. This is here. This is it, right? But remember that we have to take epsilon goes to 0. So that means this whole term here, this whole term here will also goes to 0 as epsilon go to 0. As we take the limit of the whole equation. So that means what we left in the end is just summation I equals to 1 to n, and minus 2 y minus f of xi, h of xi, plus, okay, I think here I should write some lambda in here, and plus 2 lambda integral a to b, and then f prime prime of x, h prime prime of x dx. So that thing equals to 0. Okay, so this is this equation is already simplified, and let's see what we do next. Okay, so remember that our goal here. So the goal here is that we want to write things as h of x times something equals to 0 for all h, right? And but from this equation here, right, we can see so we have to do a few tricks in order to reach this form, right? The first is that in here we kind of have the we have the point, so we have the function h evaluated at the data point xi. So it's not really a continuous function in the first term. In the second term here, we have the second derivative of h. It's not but what we want is to convert it into h of x. So there are two things to do, and let's just do it one by one. Okay, so let's just call this guy here first term, this term here second term. Okay, so for the first term here, actually there's a trick we can use that has to do with the delta function. So when we we can use delta function to convert this whole thing into integral that involves the function h. So so one can be converted to an integral with delta function. Okay, so let me just start a new page to show you how it works and what is delta function. Okay, so now let's talk about what is delta function and how we can use delta function in our problem. So, one way I'd like to think about delta function, a very nice way to think about it, it is a Gaussian distribution as the variance sigma goes to 0. So that's my favorite way to think about it. Let me just write it down. Although this way of thinking is a little bit informal, but that is a correct way to think about delta function for sure. So it's a Gaussian as sigma goes to 0. And let me just first draw a picture here. So if this is our Gaussian distribution, right? And when sigma goes to 0, we'll get a speck at exactly x equals to 0. And we don't get any probability mass anywhere else except as goes to 0. And so let me just, so for the property of the delta function, we can see we can just use these interpretations and then write out and then interpret the property directly. So delta function is usually written in this way, that so it takes a value of infinity at x equals to 0, and it takes a value of 0 elsewhere. So why this makes sense is that if we write out the PDF of probability density of Gaussian, we'll immediately see that. So the Gaussian density is something like this, right? 1 over square root of 2 pi sigma, and the exponential minus x square 2 sigma square. So when we take x equals to 0, that means this exponential term goes to 1, right? This whole thing goes to 1 when x equals to 0, and then all we left is the first term here. So remember that our sigma goes to 0, so so all we left, and then we have 1 over sigma that boils up to infinity. So this is how we get this property here. So the second property of delta function is that the integral of delta of x equals to 1. Okay, this makes sense because it is still a probability density function, even though it is kind of the limit case for this Gaussian distribution. So the third property very important, and it's actually the one we want to use to solve our smoothing spline, is that it can pick out the particular value of a function. So it goes like this. So it's f of x times delta of x dx equals to f of 0. So when we do an integral of f of x times delta of x, that's going to pick up the exact value of the function at 0. So what does this mean? Well, it turns out there's a neat way to think about it, is that if we treat delta function as a probability density, as a PDF, then what we get for this term here is really the expected value of x distributed as delta x of f of x. Right, and then remember that the distribution takes a point mass at x equal to 0. That means all the data we're going to sample from this delta x distribution are just x equals to 0. So when we take the mean of f of x, that means that gave us the value of f. That gave us the exact value of f0. So this is a property we're going to use, and then what we're going to do here is to just make a slight change of that. So consider a shifted delta function. So let's say that our delta function is shifted by xi. So delta x minus xi. If we do this with the integral of f, then that's going to pick up the signal of fxi, because for this shifted function, it takes a value infinity at x equals to xi and 0 elsewhere. So this is why So this is how we can we can convert a discrete function into an integral. So now let's apply this property of the delta function to our smoothing spline problem to see how we can proceed. Okay, now let's see how we can use the delta function to convert the first term into h of x. So let's just apply that directly. And what we're gonna get here, let me just ignore the summation sign for now. And we get 2 minus 2 yi minus f of xi, h of xi. So let's just apply the delta function integral directly as integral a to b to convert h of xi into h of x. And okay, this term here is a constant. This is a constant, so we don't need to worry about that. Then we have the h of x delta x minus xi dx. Okay, so this is nice. And from here, actually we cannot really take the function fx hx outside, but that's totally okay. And you'll see that in a second. So now we are happy. For the second term, we are going to use integral by part to convert the second derivative of h into function h, right? So recall the integral by part formula as u dv equals to uv minus integral of v du. So that's the equation we're going to use. Let's see what it leads us to. So it's from a to b, f prime prime of x, h prime prime of x, dx. So here we can rewrite h prime prime of x as dh prime of x dx. And then when we multiply this together, that gives us dh prime of x. Now let's apply the integral by part formula as f prime prime of x, h prime of x minus, so this is going to be evaluated at from a to b minus b h prime of x f d f prime prime of x. And here recall that we have the boundary condition that f prime prime of a equals to f prime prime of b equals to 0. So the second derivative vanishes at the boundary of the data. So that means our first term here goes to 0. This is nice. Let me just rewrite this a little bit as a to b h prime of x. So this is what we left. F third derivative of x dx. Okay, now we just apply the integral by part one more time by combining these two into dh of x. So that is going to give us h of x, f third derivative of x evaluated from a to b. So we have a minus sign for this, minus integral from a to b h of x f fourth derivative of x dx. So here, this term here is also going to go to 0 because the second derivative is 0 at a and b, so that means there will not be there will not be any third derivatives for this as well. So now all we left in the end is integral from a to b, h of x, f first derivative of x dx. Okay, now we are happy. And let's just bring everything together, the first and second term together. And so in the end, what we have is this equation, right? So it's going to be integral a to b. And then I'm just going to take out the hx from the two terms. Inside we have minus 2 summation I equals to 1, I from 1 to n, yi minus f of xi delta x minus xi plus, I think I'm have a 2 lambda as a constant, and then f fourth derivative of x dx. So remember that this has to hold for all function h of x, right? And now we have a nice form. So if okay, remember this must equals to 0 for all function h of x. That means the only way to make that possible is this whole thing equals to 0. So that's the only way we have the functional derivative equals to 0. So here's our equation. Let me just copy that and cancel out the 2. So what we have in the end is f first derivative of x equals to 1 over lambda summation Okay, so this equation is what we got out in the end. It is an ordinary differential equation that we can solve. Okay, I'm just going to write out the solution for this ODE and let's check if it makes sense. So fx equals to 1 over 12 lambda summation yi minus f of xi, and then we have x minus xi to the third power. So you see here, it looks very similar to our cubic spline, right? Where we kind of break it up at each point xi. And also we have a few more terms in the next, but it's not very important. So what we left is a plus. So all the terms left don't have the fourth derivative. You have some polynomials here, but for this part is the fourth derivative goes to 0. The first term is more important. Okay, so now let's just do a quick check of what does the fourth derivative of the first term looks like. And to get to that, let's just think about which term is important, right? The only term that matters is here, right? So this is a constant. This is a constant that we don't really need to care, and all we care about is this absolute cubic term. And so I just do the derivative of that. And to make things easier, I'm just gonna do this one to the third power. And let me just so this equals to x to the cube when x is greater or equal to 0, then minus x cube if x is smaller than 0. So if we were to plot this, and remember this is our normal x cube looks like, and here we're just gonna flip the negative part to the positive side. That's gonna be the absolute value of x to the third. And now let's do the derivative for this thing. So So it's going to be d dx. The first derivative for this is just 3x squared, and then this is minus 3x squared. So that's going to look something like this, I think. Okay, and just draw it in yellow. So here we just combining two quadratic functions into we just zip two quadratic functions together. Let's keep going. So the second derivative for this is going to be 6x and minus 6x. Okay, now we have a function looks like this, and then the third derivative is going to be this is 6 and minus 6. So that's gonna look like this, right? We have a jump for the third derivative. All right, now let's take a quick look of why the derivative of the jump gave us the delta function. So let's recall that delta function can be written in this way. It equals to 0 when x is not equal to 0, and infinity when x equals to 0. Right? So that's that's how delta function looks like. So at exactly x equals to 0, it blows up to infinity. And then also we have this property, right? So if we do an integral of this thing, right, what's that going to look like? That's going to give us a step function, right? So we'll have the exact jump from 0 to 1 at x equals to 1. All right, we can quickly prove that. So let me write the integral of this thing. Let me do a change of variable from x to t dt, and then from minus infinity to x, right? So that's the integral going to be. And in the first situation, when x is smaller than 0, then this integral will give us 0, right? Because delta function takes no value, takes 0 values for x smaller than 0. Okay, now for the second case, x greater or equal to 0. So this infinity can be broken apart, right? So let's just break this part by negative and positive epsilon, where epsilon is a very small number. So minus infinity to epsilon to minus epsilon here, delta of t dt plus minus epsilon to epsilon delta of t dt plus minus epsilon to x delta t dt. So the first and third term are both equal to 0, right? Because delta function takes no values in those area. And this middle part here is going to equal to 1, right? So this part equals to 1. That's a property of the delta function. So this one will equals to 1 when x greater than 0. So that gives us exactly the step function, right? So we'll have 0 when x smaller than 0, and 1 when x is greater or equal to 0. And recall our third derivative gives us this, right? So it's 6 minus 6 when x smaller than 0, and then 6 when x is greater than 0. So let's call this thing step function, right? So this is equals to step of x, right? So this thing is going to equals to 12 times step of x minus 6, which means that our first derivative will equal to 12 times delta of x. Okay, now we are getting very close. So what happens if we just shift x by xi? That means our delta function is also going to be shifted, right? So you have x minus xi to the third. That's going to give us 12 delta x minus xi. Okay, now we are in good shape. Let's just take the first derivative of the entire thing to see if it checks out. The first derivative is just going to be 12 lambda summation I equals 1 to n, and then this is a constant. You can just copy it, and then that's going to give us 12 delta x minus xi, right, coming from here. And so the 12 is going to cancel each other. Okay, now we get the exact right hand side, I think, of the ODE, right? This is the right hand side of the ODE. Okay, good. Now we checked. This is the correct solution for our smoothing spline by minimize by finding the minimizer of the functional derivative. Okay, now we are in very good shape, and let's see how we can solve the parameters for this problem. So here I have rewrite the function fx in terms of its residual Ri to replace yi minus fxi. And so you see here that the total number of parameters we need to solve are Ri. There are total n parameters for those, and then a, b, c, d. So in total, we have n plus 4 parameters. And in order to solve this, let's just plug in each data point into fx. So let me just use a different different. I'm just using the j subscript in here. So fj equals to 12 lambda summation 1 from 1 to n, then ri xj minus xi to the third power and plus the rest of the terms. Note that these are the equations, right? So in total, we have n equations for this. And then we have n plus 4 parameters. So this means we are almost there, except that we need 4 more equations in order to solve this. So this is a problem of identifiability. Means that there is not one unique way to solve this problem, and we just need to fix that. So here, let me just do an interpretation for this term a little bit. So here are our kernel terms. Note that this function here, xj minus xi to the power of third. Well, let me just remove this just subscript j here. So this is called the cubic spline kernel. And for the rest of the term are just a bunch of fixed term. So what we'd like to consider here is that we want the curvature to only coming from the kernel terms. But you'll see that in the second term here, the C and D term also contribute to curvature, and we actually don't want that just to make our problem simpler. So what we usually do is that we just usually remove those terms, and that's not going to affect how the problem being solved. So now we have we go from n plus 4 parameters to n plus 4 once we get rid of C and D. So we need 2 more. Okay, so the other thing that we can do is to add constraints to this problem. And okay, so the intuition is that we want this a plus bx term here to capture the linear part of this smoothing spline solution. So what we'd like to do here is that we want to add 2 more conditions to the R as this. As the first one is that sum of I Ri equals to 0, and then also sum of I Ri xi equals to 0. So that gives us 2 more equations. Okay, so note that there is not one unique way to do it. There are many formulations, different constraints that we can add in here to just make the problem solvable. But you know this is a common way that we do this. Okay, so the last thing that we can do here is to just write everything down in terms of the matrix notation to just bring everything together. So let's see how it works. So first thing that is that we can define this matrix K here, the kernel matrix. As this. So the Kij is going to be xi minus xj, absolute value to the third power. So that's going to be an n by n matrix. So this matrix, kernel matrix K, is actually very important, and it's going to show up again throughout this series, and we can do more interpretations on that. But now let's just finish off the matrix notation. So what we like to do here is that we can also rewrite this f here in terms of r. So we're just going to replace this one with yi minus ri. And now we can just write down the matrix notation. For this, we want something like this, right? We want the parameters. We want the matrix times parameters equals to something. The parameters that we will have are r, a, and b. So that's going to be an n plus 2 vector. And then for the matrix here, sorry, this is n plus 2. This is n plus 2 vector, and then for the matrix, we want n plus 2 times n plus 2. And then on the right-hand side, we want n plus 2 vector. Okay, so for this part, I'm just going to write it out, and you can check it out. You can check out the math by just expanding this block matrix. It shouldn't be very hard. So it's going to be I plus 1 over 12 lambda k, and then I have a 1 x, and then I have a 1 transpose x, and 0, 0, 0, 0. So here we have y 0, 0. Okay, so from here so this term here, the first row is going to give us the n equations, right? So that's going to give us the first row going to give us n equations for this, and then the second and the third row for this block matrix are going to give us the two constraints. That's correspondingly. So this is a nice linear system that we can solve easily for all the parameters r, a, and b. Okay, so that's pretty much the end of this video, and let's just do a quick summary. So recall what we did for this entire video. So first, we are starting with a functional that for the smoothing spline. Next, we want to find the minimum of this functional by setting the functional derivative equals to 0. Next, we reduce the functional derivative to get this form here to such that we have an integral of hx times something equals to 0. So that has to be held for all function h of x. And so the only condition that satisfies that is whatever inside this integral, inside this integral equals to 0. So that leads us to the ordinary differential equation. That gives us an ODE when this yellow term here equals to 0. And so next thing that we did is to solve this ODE. And so we solved the ODE And that gives us the kernel function, the cubic spline kernel. So it's a sum of cubic spline kernel. So that's our solution. And finally, we convert everything into a linear system to solve for the parameters. Okay, in the end, let's do a few remarks about smoothing spline. This part is actually important. The first remark is that why is the solution piecewise cubic? So if we look at the solution of f of x, and if we take the derivatives for the kernel part, that is the first term, this kernel part, if we take the derivatives, we notice that the derivatives is continuous up to the second derivative. So here, this is continuous. The first derivative is also continuous. Second derivative is continuous. But starting from the third derivative, we start to have these jumps. And the third derivative is constant except at each point xi. So it's constant, but jumps at xi. So this is exactly like the piecewise cubic function we assumed for the cubic spline, where the second derivative is still piecewise linear continuous function, but the third derivative becomes constant and have jumps. Okay, for the second remark, let's just recall to see where exactly did the kernel function emerge at each data point. So first, let's just take a look at our ordinary differential equations we get from variational calculus. We have the first derivative of f equals to a sum of a bunch of delta functions. So if I'm to plot the right-hand side here, this is the function gonna looks like. So this is the right-hand side. This is what the right-hand side looks like for this ODE, and you see that the function has no values, has 0 values except at each data points. So this means that, and sometimes we are calling these delta functions forcing, and we are calling these x1 to xn control points. So what does this mean is that when there are no data points, then there really are no force to push to make the curve bend, right? If we don't have any data point, we'll just have a flat curve, right? Just have a straight line. But when there are forcings, if there are data points act as force, then our curve is going to bend. And because of the curvature penalty, that acts on the first derivative of the function f. So in the end, when solving this ordinary differential equation, we get the kernel functions arising from that. Okay. Now let's look at the third remarks here. So the third remark I want to say is about the general solutions for nonlinear problems. And so our smoothing spline solution can be written in this form, that fx has the sum of the kernel functions with some coefficient ci. So it's a sum of ci times kernel function, and plus a linear term that we have. Okay, so this is a general solution for many nonlinear problems, and this function fx actually belongs to a space H called reproducing kernel Hilbert space, or RKHS. It is just a fancy name to say fx can be written as a sum of a bunch of kernel functions. So next time we're going to look at multi-dimensional spline function, and in the end we'll reach the same solution as f of x, but we'll have a different kernel function and a different RKHS generated by that kernel. So this is a general solution for many nonlinear problems. And once we've written down everything in this form, the problem can really be solved by a linear system. That's also something we're going to talk about more in the future videos.